Hello, today I will introduce some important properties of normal distribution, some of which you already know. And this is particularly important because I am going to introduce something called measures of skewness and kurtosis. So these are properties of probability distributions or random variables, but they take normal distribution properties as the benchmark. That means these skewness and kurtosis criteria are compared with the properties of normal distribution. So before we get into these measures of skewness and kurtosis, we will revisit some of the properties and some more properties I will add. Of course, I am not going to write down the formula for the probability density function of the normal distribution that you already know. I have given a list of the common continuous distributions. Please refer to that list. And there we have studied a uniform distribution on an interval AB and exponential distribution, normal distribution, student T distribution, and we have studied property, lat memory property of the exponential distribution, and we have also studied the properties of the student T distribution in detail. Now, one of the things that I have mentioned earlier in the context of normal distribution and student T distribution is that they are symmetric distributions. That is something I am going to talk about later when I talk about skewness. So symmetric distribution basically means that x minus mu and x mu minus x. So x minus mu and the minus of that, that is mu minus x, they both have the same distribution. So then we say symmetric around mu. And if mu is 0, then the definition is x and minus x have the same distribution, then they are said to be symmetric. So when the probability distribution is symmetric, then mean, median, mode, everything are equal. Of course, we are assuming mean is finite. For normal distribution, you know that mean variance are finite, and mean is equal to mu and variance equal to sigma square. In this case, the mean and the median and the mode is equal to mu. So mode is equal to mu, that I wanted asked you to verify. So how do you do that? You have to take the derivative of the density function and equate it to 0, right? What was the interpretation of the mode? Mode is the highest point in the density curve or the peak. So if the density function curve is smooth, then the derivative at that point will be 0 and the sign of the second derivative will be negative. Now, normal density is continuously differentiable because it is an exponential function, e to the power minus half x minus mu whole square by sigma square. Of course, there is a constant, but that let us ignore it for the while. So you take the derivative of this function and equate it to 0. It has only one solution, and that is at x equal to mu. So that is how you verify that the mode. Median, well, you can easily verify that y minus x minus mu is normal with mean 0 variance sigma square. Mu minus x is also normal with mean 0 variance sigma square. So it's a symmetric distribution, and so therefore the median will be mu. And the other way is that you integrate from minus infinity to mu. 1 by root over twice pi. So you see that if you make the change of scale, then what is then integration up to mu is essentially integration up to 0. So then it is e to the power minus of half of z square dz when you make the change of origin and scale. So minus infinity to 0 e to the power minus half z square dz, that is half. So therefore from there you are getting that the median is equal to also mu. So mean, median, mode are equal to this. Variance is equal to sigma square. This is something I wanted you to verify. When I asked you, I told you there is a note that I have uploaded, mean variance calculation and calculation of moments. So how do you compute expectation of x to the power k? That is, you integrate x to the power k fx dx for continuous distribution, and then you find the sigma square. It turns out to be mu square plus sigma square, and then from there you get the mean is mu. So mu square plus sigma square minus mu square, that is becomes sigma square. So this is mean variance. So for normal distribution, the interpretation of mu is that it is the mean, median, and mode, and the sigma is the standard deviation. Square root of variance is the standard deviation. Sigma is the standard deviation. So now these are some important properties of the normal distribution, that mu minus it is called 1 sigma range, that is mu minus sigma to mu plus sigma. This covers 68% of the probability. 2 sigma range is mu minus twice sigma, mu plus twice sigma, and this covers nearly 95% of the probability. And 3 sigma limit means mu minus 3 sigma to mu plus 3 sigma. যেহেতু এটা কন্টিনিউয়াস ডিস্ট্রিবিউশন, সো ইয়াত মই স্ট্রিক্ট ইনইকুয়ালিটি লিখিছো, ইকুয়ালিটি দিলেও ইট ইজ ওয়ান এন্ড দ্য সেম। Mu minus 3 sigma to mu plus 3 sigma, it is almost 98% probability. So I told you the distribution is symmetric around mu. Tar mane ki mu pora, if I go sigma units to the left or if I move above mu sigma units to the right, they have the same probability. So the curve is decaying equally on both sides of the mu. So the density curve, I told you that if you look at the formula e to the power minus half x minus mu whole square by sigma square, what will happen if I make x large? When I go away from mu, from either to the left or to the right, the density curve vanishes rapidly. Now what this is saying, that the probability is diminishing away from the mean but equally. So on both sides of the mean, the probability is distributed equally. So that is called the symmetry. Now characteristic function A2 probably I have not introduced to you, but I have introduced something called the moment generating function. So moment generating function is basically, then you ignore the I, moment, it will be e to the power, moment generating function will be just this thing only. But here I will not be there, and this will be plus. This minus is because of I square. And this will be the moment generating function. This is the moment generating. This is the expectation of e to the power tx whenever such an expectation exists on an interval on an interval of values of t, for all t in some interval e to the power tx. So that is something we had discussed. So this is the moment generating function, and characteristic function is just replace t by it when the moment generating function exists. So this is the idea. Now if x follows normal mu sigma, now why do we write the moment generating function? Because this is also another way of identifying a probability distribution. So you can identify the moment distribution through its probability density function or distribution function or the characteristic function or the moment generating function. Now sometimes it so happens that writing the distribution function is not possible. Just like for normal distribution, t distribution, you don't have a closed form formula of the distribution function. So we either identify it through the density function, or sometimes it is convenient to talk about the moment generating function or characteristic function. Characteristic function always exists, but moment generating function may not exist. For example, students t does not have a moment generating function that I mentioned earlier, because for moment generating function to exist, all moments, that is expectation of x to the power k, has to be finite for all k. That may not be the case for every random variable or probability distribution. For normal distribution, expectation of, let me write one more property here, that it my piece already mentioned korisu, so let me not. So expectation of x to the power k exists for every k for this normal distribution, and we will see what are their values. Now so if a normal x is following normal distribution with mean mu and variance sigma, variance sigma square, yaad sigma mane variance is sigma square, ami standard deviation to hai likhisu as sigma, then x minus mu by sigma, that is following normal distribution with mean 0 1. So this is called the process of standardization. You can easily prove that using the moment generating or characteristic function, and you can also prove it from the density function. That is also no big deal. So when we say that x is following normal with mean mu sigma, that is same as saying x minus mu by sigma is normal with n01. And similarly, when I say that z is following n01, add mu to it and multiply it by sigma, then mu plus z sigma will be following n mu sigma. So either way we can interpret the normal distribution. You can think of this as mu plus sigma times z, where z is following n01. Another important property of the normal distribution is that if x and y are random variable, both following normal distribution with mu1 sigma 1 and mu2 sigma 2, then take any linear combination ax plus by, that will also follow normal distribution, and the mean and sigma are mean is the linear combination of mu1 and mu2. So it will be a mu1 plus b mu2. X or y type mu1 mu2 ahibo, and variance of then this sigma square will be equal to a square variance of x, that is sigma 1 square b square variance of y plus twice the covariance of xy. A2 corpora hill. If you have looked at the note on covariance and correlation coefficient that I have uploaded in the lecture video, there I have explained that variance of the sum ki ho jai. Variance of the sum is variance of x plus variance of y plus twice covariance of xy. Tarpor I2 ahise. So now this is another number 10. This is very important property, and particularly for normal distribution only. I had told you that if x and y are independent random variable, then covariance is 0. Kintu opposite to true no hoy. Tar mane covariance 0 hole x y independent no hobo pare. We have a counter example that x takes plus minus 1 with probability half and y is equal to x square. Tar covariance 0 hoy, kintu y is x square. So they are not independent. কিন্তু এই ক্ষেত্রে যদি মই কই দিউ যে x and y are following normal distribution, then covariance equal to 0 will imply independence. And of course independence means, so covariance equal to 0 means independence only for normal distribution. Okay, aru etia ahil kotha to jitu moi agot koisilu je normal distribution or karone all moments exist kore. In fact what we can show is that x minus mu to the power k is 0 for all odd number. So if you are looking at deviations from mean, mu is the mean, take any power of that, average out, it will be 0. এটু কিও হয়, এটু এই প্রপার প্রিসাইসলি সিমেট্রি টুর কারণে হয়, কারণ তুমি যেতিয়া x মাইনাস মিউ লোৱা ইয়াত হল মাইনাস k সিগমা তার তলর ভ্যালু বোৰ আৰু x মাইনাস মিউ তার উপর k সিগমা ভ্যালু বোৰ, so they have same probability, so they cancel out each other. So large deviations from mean, the positive deviation and the negative deviations have same probability, so they cancel out each other. And finally ahile tomar jodi moi even power law, then of course it cannot cancel out each other karon tat kono negative value nai tetia, and the result is that is sigma to the power twice k or variance raised to the power k, or twice k hol hobo 135 twice k minus 1. So etia tomalokok moi et exercise dilu je suppose what will be x minus mu raised to the power 4. So let me add another exercise, that what will be x minus mu raised to the power x minus mu square to ki manobo, that is obviously sigma square variance, aro a2 raised to the power 4 kori dilu, so that will be how much? So that you tell me. Okay, type kora is extremely difficult, so you have to tell me what is the formula here. So how much? Okay, so these are some important properties of normal distribution. I want you to carefully study them and solve this problem. Aru a2 keneke ulabo x yat mu aru sigma 0 aru 1, tar mane tumi a2 list joa yat sigma aru sigma a2 hol 1 a2 hol 0, so tomar khudise je x greater than 1 kiman hobo, so hetu keneke ulabo, so x greater than 1 mane ki, so x is to the yat ase x is between mu 1 sigma 0 hole x between mu 0 sigma 1, here mu is 0 sigma is 1. I am trying to speak a bit quickly because I am recording this, I have limitation of time. So mu 0 sigma 1 hole this is x between minus 1 and plus 1 whole iman. So the tar complement to ki hobo, what will be the probability of complement of that? That will be x is either below minus 1 or x is above plus 1. Now you also, so you have to use property 3 and 6 carefully. So a2 yar pora ulabo aru ei duta ulaba, and also this will be relatively easier. So what will be x minus mu greater than twice sigma? This will be just a complement of this probability, so this will be 1 minus this, because what is this? This is equal to 1 minus probability of x is between mu minus twice sigma to mu plus twice sigma. So a2 prothomot koriba, moi already I have given it exercise 1, you do exercise 2 first. So what will be x minus mu greater than 3 sigma? So you will see x minus mu greater than 3 sigma is 1 minus that x is between mu minus 3 sigma, and you can see this will be very small probability. So you see for normal distribution, for values exceeding 3 sigma limit, either above 3 sigma units from the mean or below 3 sigma, that is extremely unlikely. So normal distribution, although this is the distribution that can take any value with a positive probability, any range with a positive probability, in practice actually the most of the values, 99.73% values are between mu minus 3 sigma to mu plus 3 sigma. So a2 limit or bahirot thakar probability to khub small. Similarly mu minus twice sigma to mu plus twice sigma মাজত কিমান দিয়া আছে ইয়াত 95% ভ্যালু আছে